Oh, well, you don't work right now.
I work at the Simpson.
Oh, don't you have that?
And the only way I knew about it is because.
Okay. It's 9:30. So today we are going to cover an example of HLSM. So Mark told me that many of you guys don't know what HLSM stands for. Can someone tell me what HLSM stands for? Can someone else tell me what it stands for?
High level state.
Okay. So, just want to make sure that we're clear on this. Because I'm pretty sure you guys know what it stands for. Okay. So high level state machines. We've been talking about them for like 3 weeks, right? Here is our practice problem for today. We're going to do it in multiple steps, just like how your homework and quiz will be. So you want to design a controller of a car that can do this adaptive cruise control. So the car will always increase its speed in the safe region by 1 meter per second every single cycle, unless the distance d of a car in front of it is less than 64 meters. This is called the risky region. And when it's in the risky region, the car will reduce its speed by 4 meters per second. If the distance is less than 32 meters, this is the danger region. And it will decrease its speed by 8 meters per second until it is no longer in the danger region. So the resolution of the distance sensor is 1 meter. So that will tell you how many bits these things need to be. And the clock frequency is just going to be 1 hertz. And the car will start this cruise control by switching it on using the R input. So the R input is just going to be like a button used by the user to start the cruise control. So this is your description. Here is an initial high-level state machine diagram. Now we need to fill it out. So your code for today is 595. Answer it immediately and do work with the people around you immediately. When you have this high-level state machine filled out, then change your answer from A to B. So when you answer immediately, just answer A. And then when you're done as a group, change your answer from A to B. 595. Who's answering E? Whoever's E, please change to A.
Either if you're risky or safe, straight to danger, or less than 32%. If you're still less than 32. So yeah. If you receive these things. So then the car seat, the lowers and the stuff, and the but if you're in the risk, car speed wide, will decrease by 4 meters per second. If you're in the danger region, there was a decrease by 8 meters per second. That's the.
It seems half of you are still not done, but in the interest of time, we do need to start going over this because there's still part 2 of this question. So, first, what are my inputs? R, D, how many bits is D? It needs to go up to 64. So I only need 6. Okay. But 7 is more than enough. So if you put 7, that's fine too. Okay. Minimum is 6. So let's just put 6. And do we have any other inputs? What's our output? How many bits? It doesn't really specify how many bits we need. It doesn't specify a max speed, right? So let's just set it to something reasonable. If we have a distance that's 6 bits, let's just set our speed 8 bits. So this is something, because it's not specified, we'll just be flexible with it. Okay. And do we need local storage? Yes, no? How do we remember what our speed is? Our current speed? Local storage. We are going to store speed. Okay. And now the transitions. Well, let's just fill in the states first. If I'm in safe, what happens to speed? Right? If I'm in risky, what happens to speed? If I'm in danger? Right. And some of these transitions are already filled for us, but when would I go to risky from safe? Need both of these to be true, right? And then when would I transition from risky to safe? Risky to danger? Danger to danger? And then safe to danger? Right? Do I need any more transitions? I don't think so, right? Okay, next step. Draw the data path. So you have an adder already, and you have register for speed. So now, when you're done, and again, just work in groups, change your answer from B to C. Let's work on this for about 2 more minutes, and then we have to move on.
testing.
Mhm.
Does the 8 signify it's 8 bits? Or wherever you see 8,
Mhm.
so wouldn't we change distance to 8 bits, not 6 bits?
Is 8 enough? 6 is enough, right? So 8 is more than enough. Right? Okay. So again, not all of us are finished, but we do have to move on in the interest of time. So what do we want to add here first? It doesn't matter what just tell me what you've added. Doesn't matter what's first. Okay, what do we need to be able to increment speed by? One, and what do we need to be able to decrement it by? 4 and 8. So I have 3 things. I have 1 input into this adder. What does this mean? What do I need to add? I have 3 choices. It needs to go to 1 thing. Yes, mux. Here's my mux, right? Inputs, I have 1. I have 4. I have 8. What is this for? How do we reuse an adder as a subtractor? We use the same thing, right? So this is for telling us if we want to do addition or subtraction. So where should this go? What's going to set this?
Yeah.
I need to be able to increment or decrement. So it's not always going to be 0.
If it's 0,
This needs to go to the controller. The controller is going to set this signal. So it's coming from the controller. Okay. What do we need in order to select these values in the mux? How many bits? Say this is 0, this is 1, this is 2. How many bits? I have 3 options. How many bits do I need? 2, yes. Where is this coming from? Who tells this mux what to output? What process is that? You're so close. It's based off the distance, but the distance decides what? The state. So the state is part of control. Yes. Control is going to decide which input this is going to be. Okay, so now we can increment, and let's just give this signal a name. What do you want to call it? I'm just gonna call it select, SEL. And then this other output of control, if it's gonna subtract or not. Okay, it's just one bit. What else do we need? Someone said it already before. Yes, compare. When are we safe? Double check, yes. So this is our comparator. Now we need to input D. Right? When are we in risky? When are we in danger? So that's to safe. This outputs to risky. This outputs to danger. Right? Do we need anything else? Are you sure we don't need anything else? Where does that go? Yes. What else? Something very critical missing. Yes. We're not outputting anything right now. Right? Now we're outputting. Okay. We have our three comparators. We have this mux to select. If we're going to add 1, 4, or 8, and then we have the control for the adder to tell us if we are going to add or subtract. So this is our data path, and it's also connected to control. Right? So now that we need to draw the finite state machine. We don't have time to do this alone, so let's do it together. First state, S0, was called wait, right? So this is our initial state. We stay here if so R not, right? We go from wait to my circle is not. I need more space. Okay. To safe initially if R is 1, right? And in S0, what needs to happen? Oh, we're missing some other stuff here. I forgot. Load clear. Okay. So when we're in wait, clear is 1, right? It's not important to set anything else, right? So they're all assumed to be 0. If we're in safe, what needs to happen? Load is 1, right? And we need to increment speed by 1, right? So what needs to be our signals here? What does select need to be? Select needs to be 0 to select 1. What does sub need to be? If we're calling it sub, yeah, it should be 0, right? Sub is 0. And what else? Let's just also be clear that clear is 0, since we have space in there. Okay, so we have these 2 other states. Risky, danger, right? I go to from safe to risky when? Yeah, so what does the controller know about though? When B is 1, yes. So A naught, B, C naught. Right? We stay in safe if A is 1. We go from safe to danger when? We go from risky to safe when? Someone else, I stay in risky when? I go from risky to danger when? Someone else. Danger to risky. Huh? I think you mean this, but you said something else. Wait. Okay. Right. Yes. Okay. I stay in danger. I heard something else. I'm sorry. Okay. Yes. This is all of our transitions, right? Correct? I want confidence from you guys. Yes or no? Our transitions. Okay, now are we done? Confidence. Yes. Okay. But we need to specify our outputs inside of these states. What does load need to be in the risky state? What does select need to be in the risky state? What does sub need to be? What does clear need to be? What does load need to be in danger? What does select need to be in danger? Yes. What does sub need to be? Clear. We're done. Yes? We have description, high level state machine, right? Data path, as well as the connection between the data path and the controller, and the finite state machine implementing the controller. Right? These are all of our steps. From the memory lab, we know how to now make this into VHDL. Right? How many files for the controller? 1 plus maybe a test bench. Yes. For the data path? 1 plus maybe a test bench. For top level, which is data path plus the controller. Top level. 1 definitely a test bench, yes. Okay, so this was review for high level state machines. You have a quiz on Wednesday. It's going to look very much like your homework. I am not going to be providing you with this templates to get you started, just like the homework does not, right? You have to figure it out. I will not be providing a data path template. Again, you have to draw what you need, okay? And if you need to draw the controller, you know how to draw the controller from the previous 2 things, right? Okay, so the other thing that we should talk about is Memory Lab was due. Memory Lab has been graded, right? Most of you did fairly well, which is good. Because if you can do the Memory Lab, you can do the final project. For those of you that did not end up with a correct implementation, if you want to be successful on the final project, I recommend that you still work on the Memory Lab and finish it. And if you need help and you want more guidance beyond what we've already given, you can come to me or Mark and we can walk through the solution with you. We will not provide the solution for you, but we will walk through it. You can see it and you can see how it was implemented. But then you go back and you work on the file on your own again. Okay? So that's how we are going to want to help those that need a little more help on this memory lab. Okay? And also, if you did it and you're just curious to see a different implementation, because most likely Mark's implementation is a little different than yours, you can come see it too. Okay, so if you want to see that, you have to come see us in person. So either come to my office hour or make an appointment. I don't know when Mark has office hours, but same thing. You can email him to try and make an appointment if you want to talk to Mark about it, or go see him during his office hour. Or you can email me if you want to talk to me about it. Okay? But this is your last lecture from me on new content. Wednesday is your second to last quiz on high-level state machines. Your last quiz will be on pipelining and unfolding, which we already covered, right? And that will also be your last homework. And then every single lecture meeting after that is to work on the final project. I will still be here. We will still have Pull Everywhere codes for coming to lecture for participation. And that is all. Okay. Okay, I'll see you guys on Wednesday. A reminder that there is no class on Friday. Okay, Friday is Veterans Day observance because Veterans Day is Saturday.